In this segment, we're going to look at key concepts 2 and 3 of VSEPR theory to see how lone pairs and multiple bonds impact the geometry about a central atom. If you recall, key concept 2 says that lone pairs of electrons will take up more space than bonding pairs. In the figure shown, you can see that that is in fact the case. The bonding pair is much more localized between two nuclei versus the non-bonding pair takes up more angular space about that central atom. Now, let's think about the reason why. The most important question we need to ask ourselves. Why would a lone pair take up more space than a bonding pair? Well, think about a chemical bond. It's that perfect balance of forces. We have that attractive force of the two electrons to both nuclei. And that attractive force is what causes those electrons to be in that smaller space. They're more attracted to the nucleus, they are going to be closer to that nucleus. Then we have that opposing force of the nucleus and the nucleus, both positively charged, and then we have the opposing forces of the two electrons. Those are oppositely charged as well. So it's really that favorable force of the electrons with the two nuclei that causes the chemical bond to form, that causes those electrons to be more localized. The fact that the lone pair is only attracted to one nucleus, that attractive force is much smaller, so those are going to be farther from the nucleus and take up more space. All right, with that being said, we can start to look at how that impacts the actual bond angles about a central atom. So we know that in a tetrahedral geometry, the bond angles ideally are 109.5 degrees, and that is a number that you need to know. So if we look at methane here, this carbon atom has 4 domains. They are all bonding domains, and so this will be 109.5 degree bond angle. So what might happen if we know that lone pairs take up more space? What would happen to the NH bond angle here? Would it be larger or would it be smaller if this lone pair is taking up more space? Well, this angle would be smaller because this lone pair is squishing these bonds closer together. All these electron groups are repelling one another. Because the lone pair is taking up more space, it's repelling those other groups more than the other groups repel other groups. So this bond angle will be less than 109.5 degrees. And if you measured the bond angle, you could see that it's 107 degrees, in fact less than. But I'm not going to ask you those specific numbers. If you can identify it as less than 109.5 degrees, you are good to go. What if we increase the number of lone pairs? Well, here in water we have 2 lone pairs. So those 2 lone pairs will be taking up more space, and the repulsion between the 2 lone pairs is going to be greater than the repulsion of the 2 bonding groups because they are taking up that increased amount of space. And so this angle will be even less than 109.5 degrees. And if you measure the bond angle in water, it's 104.5 degrees. So again, you don't need to know those specific numbers, but I'm just citing the experimental evidence that we know for a fact that these angles are less than 109.5. For your purposes, you just need to know that the angle will be less than 109.5 due to the deviation from that ideal angle because of those lone pairs. Key concept 3 of VSEPR theory says that multiple bonds will take up more space about that central atom. If we look at this compound, and we see in the structure that there are 2 bonds between carbon and oxygen here, those 2 bonds are made up of each 2 electrons, so these 4 electrons mean that there's more electron density here, which will result in more repulsions between neighboring groups. And as a result of increased repulsions, these bond angles are going to be distorted from their ideal angle. So do we remember what the ideal angle is for trigonal-planar geometry? The steric number here is 3. We've got 3 bonding groups about that carbon. So that would lead me to see trigonal-planar geometry. and that has ideal angles of 120 degrees. So if we're taking up more space and have more repulsions here, this angle, should it be larger or smaller than 120 degrees? Well, it should be larger than 120 degrees. And in fact, it is 124.3 degrees experimentally. So we know that that is in fact the case. Now, what would be the case for this angle down here? If this is greater, how about this one below? Well, the fact that that's larger, and we know that this has to make up a circle, right? So the angles all have to add up to 360 degrees. So this angle would have to be less than 120 degrees. And if I check my sources here, it's 111.4 degrees. So that's quite a big difference from ideal behavior. And likewise over here, we would expect greater than 120 degrees because that angle does include the multiple bond. So we can say that angles that include the multiple bond, such as these two, will be larger than the ideal angle. And then angles that do not include the multiple bond, there has to be one present about that atom, but this angle, the Cl-C-Cl angle, doesn't have a multiple bond in there. So that angle has to be smaller than the ideal angle. At this point, we are familiar with all of the key concepts of VSEPR theory. One, that electron domains will want to be as far from other electron domains as possible in order to minimize electron-electron repulsions and maintain the lowest energy configuration. Two, that lone pairs take up more space than bonding electrons. And three, that multiple bonds take up more space due to the increased electron density in that region. So these all have implications on the electron domain geometry that we observe and the bond angles that we see in molecules. So as you're practicing and predicting bond angles, if you have questions, please let me know. Thank you for watching.